starting. Okay, we're live. There we go. And now we're live. So I think we're ready. We can start. Sometimes people come in a little bit later. Don't let it distract you. Just FYI, guys. So Pankaj was an organizer of a different meetup. They were, I guess, running in parallel, but started way before we did, and a very successful group as well. And he already made this presentation and many other presentations on other chapters for them. So this is not a dry run. He's a pro.
No, not by any means. Yeah.
And he'll be able to tell you more, obviously, about what he's up to and what he's doing in machine learning and life.
Sure. So I'm Pankaj. I'm a software engineer with a big interest in machine learning. And we have been working on this project called Data Cabinet, which is online with Conda environments. So I would encourage everyone to check it out. You can keep your code and your environment right there. You can, like I'm running this presentation from there as well. I haven't done the best presentation, so this is not the best sample, but you can do better presentations using notebooks and Conda environments. So I'll just get started. And project. Oh, okay. I thought, sure. So I'll also go back and forth between the notebook and full screen. So linear factor models, they are a way to, they can be thought of as a way to find a probability distribution given some data. So if you think it's a way of modeling a probability distribution given data, and if you have the correct probability distribution given some features, you can predict the rest of the features, and you can that's where it starts with. But if you try to do that, generally you would find out latent variables in the data, which is denoted here as H. So for example, if you have a data image, then whether there is a zebra in the image is a latent variable in that probability distribution. If you, given that like, let's suppose you factor in given H, you factor in the conditional probability of X, then the probability distribution can also be thought of as the expected value of over the latent variables if you model the conditional probabilities. So and the way H is modeled in linear factor models is a simple joint. So if you can get an H with a simple joint probability distribution, so like a factorial distribution where each H, so for example, if you're going from a 100-dimensional space in X to a 5-dimensional space in H, then each of those 5 are independent of each other, and they can be, the probabilities can just be multiplied together. That's how linear factor models is modeling H generally. And so there are two basic things that go for linear factor models. One is that there are 2 steps, encoding and decoding. You go from X to H, so like a higher dimensional space generally, to a feature space, and then back to X. So going from H to X is generally just a multiplication, a linear affine transformation plus some noise. And going from wait, there was one more. yeah, the factorial distribution and the affine transformation to get X. These are the two things that are common to all linear factor models. And so the first one we can discuss, the first method to do it is factor analysis. So in factor analysis, you kind of assume that all your H's are come from a multivariate unit normal. So you're modeling your H like that. And if you see, the noise is modeled as a diagonal matrix. So if you see with different values in different components. So for like if X is 20 dimensions, then each dimension can have a different value for these sigmas. And if you model your H like this, so then you you're kind of modeling X so that given H, X is conditionally independent. And if you just do a direct substitution, then you can also think of, if you find out, for example, given X, you find out the W and B and noise, then this can be just, X can also be thought of as just sampling from normal distribution that is centered at B and has a covariance matrix. This is the covariance matrix. So it's a, if you look at this link, like you'll see it's a multiplying a unit multivariate unit normal with a W leads to this different multivariate normal. And so that's factor analysis. Then probabilistic PCA imposes one more condition on factor analysis, which is that all these sigmas are the same. So if you consider all these sigmas to be the same, then it becomes probabilistic PCA. And if you see, if you know PCA, then if this is 0, if the sigma is 0, then it's basically PCA. But even if you model it as a probabilistic PCA, given an H and given some data, there are algorithms like some expectation maximization algorithms that will figure out the W and sigma for you. So you can, given some data, you know what dimension to take it to. It can figure out the weight matrix and the noise to add to it. So if sigma is 0, it becomes a plain PCA. But otherwise, this is probabilistic PCA. So then the third way to do it is independent component analysis. So the main difference between, so in these two methods, factor analysis and probabilistic PCA, if you see, they are, the H's are supposed to be like decorrelated. So which means decorrelated means they don't have a linear dependence on each other. But they could have like a different dependence. They need not be independent of each other. So the classic example is like points on a circle. They're not like the X and Y are not independent of each other, but you can create examples where the correlation is 0. So here we are only assuming the correlation is 0. But in independent component analysis, you are assuming, you are trying to make the H's independent of each other. So you can also think of like a practical example that the book gives is like if you are recording output of a microphone and there are 5 speakers, then independent component analysis will try to figure out what each speaker is saying. So there are 5 H that lead to 1 X. So it will try to figure out the individual independent components of X. And so there are multiple ways to do ICA, but there are some commonalities and some notes that the author makes on about these. So generally, he says that it's not a generative method. So it's not like they're trying to figure out a distribution on H or X. They're just trying to make make a transformation from X to H so that H remains independent, that H can be made independent. And so generally, it will not do like a maximum likelihood, but try to get this H from X such that H is independent of each other. The components of H are independent of each other. And also, if you see this transformation, this needs to have a Jacobian of this. Like if you take a random, yeah. Yeah, sure.
So, I didn't know if I turn the lights off to have higher contrast on the bottom screen.
Yeah, sure. Is this good? Okay, so this one is trying to find a W that makes H look independent of each other. And so one other thing is that when you assume a distribution on H and you try to change the distribution, then you cannot do it. Then you cannot just do it directly. So one example that the book gives is if you, for example, have a uniform PDF of 1 from 0 to 1, then if you change y is equal to x divided by 2, and then it will not sum to 1 if you do the direct substitution. So you have to multiply it by the Jacobian. And if you see here, W is the Jacobian of dx by dh. So you need to find out the determinant of that Jacobian to be able to make that substitution. So to do that, it doesn't go into a lot of detail, but this is what it gives, that W is generally, they try to make W to be orthonormal to each other, which is like unit length 1 and all the columns are orthogonal to each other, so that the volume is 1, the determinant is 1 or minus 1. So that's another thing that they try. And also that the assumed distribution H they try to make it non-Gaussian, because for Gaussian you cannot get like a unique W if you model it as Gaussian, because other methods all model H to be Gaussian. But here they are intentionally trying not to make H Gaussian, because Gaussian, if you assume Gaussian, then this H, for this you'll get more than one W that satisfies that condition. So so that's why they also try to get pH to have larger peaks, have a distribution with larger peak near 0, so that it has some feature selection, sparse feature properties. And so one method that it mentions is like, because it's trying to not make it Gaussian, so to do that, it actually tries to increase the way it is such that when you transform H to X, the kurtosis of H is very high, so it will not be Gaussian. So kurtosis is the fourth moment, Gaussian is the second moment. So you're trying to make such that so that's one method to do independent component analysis. And kurtosis, because it has higher kurtosis, it also leads to higher peaks near 0. So it also leads to feature selection. And so there is, you could do other things with it as well. So so this, if you see, this is basically a simple transformation for which there is a simple derivative. That's why this transformation is being chosen. You can even stack multiple of these with some non-linearities in between, as long as it's easy to invert them. So that way, the book mentions there is another method called nonlinear independent component estimation, in which if H and X have a nonlinear relationship, then this can figure that out. And Then there is independent subspace analysis, in which here in ICA, all edges they're trying to make all edges as independent of each other. But in this one, what you do is you get groups of edges which can be related to each other, or have like a higher than zero correlation, or they can have some relationship, but the groups together don't have any the groups together are independent of each other. So that's ICA. And yeah, okay. So the next method that the book mentions is slow feature analysis. So slow feature analysis builds on a principle, slowness principle, which the book explains in like a video method. So if you have like a bunch of pictures, one after the other at multiple times, then you can have, that's what it's trying to model in this example generally. So for example, if you have a video in which a zebra is moving from left to right on a screen, then if you just measure individual pixels, they will go from white to black very fast. But if you put it to a feature space that of zebra's location and zebra's presence in the view, then it will be those two things will not move very fast. So the zebra's location will only move slowly, and the zebra's presence in the video will not even move. So this fact is being captured by slowness principle. So if you, for example, want to put your image into a feature space of zebra's presence and zebra's location, then what you could do is you could basically put this optimize on this loss function. So let's suppose f takes an image and gives out the zebra's location and zebra's presence in the picture, and then you get it at the last in the previous picture, and then you put a loss function, for example, the mean squared difference of zebra's location, and you scale it by some sigma, and you sum it over time, and then by optimizing this, you can get parameters of f. So then you can get, if you find f, then you can bring x down to zebra's location. So slow feature analysis uses slowness principle, and it uses a linear extractor. So if you think of this as f as a linear transformation to the picture, and then you are trying to figure out all the parameters of this matrix, then this becomes slow feature analysis. So the way slow feature analysis is formulated is something like this. So so think of it as like the ith feature. It's trying to get the ith feature between every timestamp and get the difference of it, square it, and minimize it. So what happened here? Okay, so then so there are a couple of things to note here. One is that the expectation of each feature is supposed to be 0, because if you, for example, each feature it's not centered around 0, then you can move it. These values will remain the same, so you won't be able to actually compute it. So if you have a feature, if x goes to a feature that is not centered, then that is centered, then you can have unique fx's. Otherwise, you can move by a constant margin. The second thing is that the square of at each time step, the So this is a funny one. At each time step, the square of the linear transformation should add up to 1. Can you see why? Why should it add up to 1? What if it does not add to 1? What if this constraint was not there? Like, you take a picture, you find a feature, let's suppose, and let's suppose the location, which is a number, and if that is not, and you are trying to minimize this, if the sum is not, if you don't put this constraint, what might happen is it will put all f to 0. Like, it will just, the transformation will be to 0. So then this will be minimized. So you have to make sure that the transformation, the sum is 1. So then there's another constraint that it puts, is that the correlation between the ith and the jth feature should be 0. If you don't have this constraint, then what will happen is all the features, all the h's will try to model the same feature. So the slowest feature, all HIs will basically start modeling the slowest feature. So that's why we have this constraint, which is if xti and xtj should be 0. So the correlation between them. So the book also mentions that you can use it in to capture nonlinear relationships as well, but you take X and you make like a nonlinear transformation to it, expansion to it first, and then like quadrat, like you take X and replace x1, x2, x3, x4. You replace it by x1 multiplied by x2, x2 multiplied, like all possible multiplications, and then you put SFA on top of it. So then it can capture some nonlinear relationships as well. The book mentions that SFA has some biologically plausible representations, like some neurons in frogs or something behaves like SFA does. And it also is that SFA, it's possible to theoretically predict what features it will learn. So for example, if you have a scene in which a camera is going and recording a space, then SFA can learn the location and velocity of the camera. So which basically is a linear thing. So that's why it can do. But the book kind of mentions that this hasn't become very popular because the slowness prior is not very is very it's restrictive, because the slowness prior is not does not explain everything, I guess. So there could be better priors that it goes through. So that's SFA. Am I going too fast, or?
Can everybody hear also in the back?
Okay. Cool. So that's slowness principle, and then there is sparse coding. So this is little different from the previous one. So if you see, in the previous one, you got W. So if you see this, once you get W, then you can just sample. So X comes from, it doesn't depend on H itself. But here, probability of X given H is this normal, which depends on H. and you assume a prior, like a Laplace or Cauchy or one of those distributions that has a peak in the at 0, so that you can have more of a you can have feature selection. So in this one, what you're trying to do is, given an h, given x, you're trying to find the x that gives the maximum probability of p of h given x. So you're trying to find h for every x by running. So if you take these two and you try to unroll this, then it becomes maximum of log of p of h, because log is a monotonous function, and then it becomes an argmin of lambda h plus beta of x minus wh whole square. If you take Laplace, then this is the argmin that you will get. So given x, you're trying to figure out w as well as h. So given a bunch of points, you're trying to figure out this weight and this h as well. So the representation as well as h. So every time you're given x, you're trying to compute h by using this method. And this is, I forget which method. Yeah, so the training alternates between encoding the data and training the decoder to better reconstruct the data given. So the training does both encoding and decoding at the same time.
I have somebody from online world is asking about what W stands for.
W is this. So W is the. So when you try to decode data, you generally go from Wx, so Wh plus B. So in all linear factor models, you go, W is a matrix of weights that goes from H to X. So let's suppose X is a 30-dimensional vector and H is a 5-dimensional vector. Then W will be a 30 cross 5 matrix that will take that 5-dimensional vector to a 30-dimensional space. And so here the Laplace, and so in this one, I don't have a very good grasp of this, but in this one, there's an algorithm that runs every time. So it's not like you find like a W and then just multiply every time you see a X, you multiply by that W to get H. In this one, you can you have to run an algorithm to figure out what the H is by optimizing. So and also that if you see, this is trying to argmin on H1, the first norm of H. So it induces sparsity. So only a few features are selected, not all features get selected. So then that's how you get H. So the good thing about this method is that even if you get data that is not that is not in the training data, then you run this algorithm again. So it doesn't it can still learn the features. It can still figure out the smaller representation better. But if you, for example, have one of the other methods, then if you give it some data that is not in the training data, then it will not work very well. So and the disadvantage is that it's hard to train and it takes longer, more compute to train to get H, because every time you are trying to optimize this to get H and even H. So that's sparse coding. So sparse coding there's also this thing that in some of the other methods you could sample from, like if you figure out the distribution of H, you can sample from H and then come back and make some representative data X. But here it's not possible to do that because the Laplace, it's not possible with a Laplace prior because it will give it doesn't have zero value anywhere. So like a Laplace prior will have values for each different H components. So that's why it's hard to sample from it. So there is a paper by Ian Goodfellow. They call it the spike and slab sparse coding model. And using this, they can sample from the distribution they have found to generate X. X is the origin. X is like a sample data. So that's what they're doing here. In this picture, they're trying to generate some data by sampling from H. So they got some data. They figured out all these W and H and beta parameters. Now they're trying to generate some data. But if you see, they took MNIST data and tried to generate. It doesn't look like representative data. So the reason they think that it's not very good because of the assumption that all H components are independent. So what the book says, what happens is every component gets a different feature every time. So it need not, because you train like for every point you train again. So you get like a different set of features for every data every time. So that's why it doesn't look like it. Although you can go from X to H and to a lower dimension and then go back to X. Okay, you cannot generate this data well using this method. So that's what this picture is. And so the last one is a description of PCA. So the book says PCA is basically principal component analysis, and probabilistic PCA that we just saw here was like you're modeling a WH plus B. In PCA, you're generally just modeling WH plus B. And in probabilistic PCA, you put like a constant error, a constant noise as well. And the book says that in probabilistic PCA, what you're trying to find is like a manifold which is on the shape of a pancake. So by that, let me. So basically, if you see, if you project to the maximum variance plane, any like a 3D set of points to a plane in a 3D space that has the maximum variance, then it will be like an ellipsoid, and which the book calls a pancake shaped manifold, and then so okay. And if you formulate the PCA problem like this, that H is you take X, you find out some mu and W that takes it to a lower dimensional space, and then you find another matrix and B that takes it back to the original space. And you're trying to figure out what the expected. You are trying to minimize the reconstruction error, which is this expected value of X minus X bar, the whole square. And so if you try to do this, then what you will get is V and W are the same. And you will also get that so you're trying to project to so if H is, for example, only one dimension, then you're trying to project X to the axis where it has the maximum variance, which is going to be the principal the direction of the principal eigenvector. If H has two components, then it will be the first eigenvector and the second eigenvector, which has the second highest eigenvalue, which is orthogonal to the first one, and that so those two. And if you break X into three matrices, V sigma V transpose, and if you do that analysis, then you will see that this expectation of the reconstruction error is going to be the leftover eigenvectors. So basically, let's suppose W has X has a rank of 5, so it will get 5 eigenvectors. And if you take four of those, then the remaining eigenvalues will be the error in the reconstruction. So that's all the methods that for linear factor analysis. So like it's a way of analyzing data. Like it's a way of formulating a probability distribution over X, and it generally gets to finding latent variables and imposing priors over those to reconstruct X. So that's all in the chapter. If you have any questions, yeah.
Could you go over why the difficulty sampling or like generating samples from sparse coding model? I don't think I quite understood that.
Which one? Sparse coding?
Yeah, so sparse coding, where you're looking at the image from Agnes, you're talking about difficulty sampling property.
Sure. So basically, you're running the whole algorithm every time you're getting a point. You're running the whole algorithm trying to find the H. And H is the same feature. It does not like the first. So H is like 5 dimension, right? So it's not like the first dimension. Let's suppose the dimension that is most important is the location of a zebra in an image. Then the first dimension will not always be the location of the zebra. It could be first. It could be the zebra could be the first one in one go. For one sample, it could be the location could be the third H3 for the second sample.
So we don't like take an H and then generate X from that. For every sample, we're actually kind of retraining it and determining the relationship between H and X.
Yes, yes. So that's why like when you try to generate it from this model, then it doesn't come out to be very legible. Any other questions? Do I use PCA? I've used it for class purposes, yeah. I'm sorry? I haven't used them a lot, yeah.
Any more questions for the presenter? I know we're going to zoom through this. It's a lot.
Just to clarify, the difference between probabilistic PCA and PCA is just that in probabilistic PCA, you assume there is error and that error is fixed.
Yes, error is fixed in every dimension, and in PCA you are trying to just you're trying to get the planes with the maximum variance. Okay. Cool.
Thank you.
Oh, thank you. Thank you.
Before we move on to town hall, is there more questions? Wait, Francis, you look like you. GPS. Okay. Just to kind of give you guys a refresher, there's only 3 more sessions left, sadly, but then we'll be done with the book. So next, and they're like kind of crazy. So we're gonna do GANs next. So chapter